for the next part, we'll be going into total internal reflections. Okay, we'll be learning about the terms used, which are critical angle, as well as the conditions for total internal reflections to take place, and then some of the applications of total internal reflections in our optical fibers, specifically in the use of telecommunication and medicine, and what are some of the advantages of using optical fibers. Okay, you can see this very often. You can see that there's a fish in the water, and if you look upwards at the water, you can actually see a reflected image of the fish under the water. All this happens is because of total internal reflections. Okay, so what exactly is total internal reflections? Let's take a look at a series of diagrams. Okay, so first, you have a ray box. Okay, the light rays shine through this semi-circular glass block. Okay, the light ray enters. As the light ray enters from air into glass, there's no bending because the angle of incidence is 0. The angle of refraction is 0. The light ray is shining along the normal. So there is no bending of light over here, although the light slows down. And then if I were to shine it straight, okay, at the part where it exits the glass block, again is along the normal. So again, we say that the angle of incidence is 0, angle of reflection is also 0. There is no refraction taking place at all. But what happens if I were to shine the light, I were to shift this ray box in this direction anti-clockwise, I am increasing at this point where it enters the glass block, again is along the normal. Can you see that there is a 90 degrees? So it's along the normal. Again, there will be no bending, no refraction over here. So it will just go straight into the glass block. But at this point of time where I hit the glass block, I am not along my normal. My normal is this dotted line. Okay, so there is an angle of incidence over here. So I'm going to draw. There's an angle of incidence here. So when there's an angle of incidence, okay, there will be an angle of refraction when I come out. So when I come out of the glass block, I will bend away from the normal. Okay, because it's less dense, optically less dense. So as I increases, R also increases. So I continue to increase this I, continue shift. Okay, this R will increase and increase and increase and increase some more and more and more. Okay, other than refraction, there's also a weak partially reflected ray, because some of the light hits this surface, some of the light gets bounced back. So there's a partially reflected ray as well. Okay, but I will increase until this angle I can be increased until I reach a particular angle. Okay, this is a very special angle such that my angle of refraction will also increase until my angle of refraction in this case is very special because my angle of refraction is 90 degrees. The light ray travels along the glass block. Okay, in such a case, okay, this very special angle, okay, we call it the critical angle. Okay, so when we say that when the angle of incidence over here becomes equal to the critical angle, the angle of refraction will become 90 degrees. Again, there is still a weakly reflected ray. Okay, but that is just a very small. Okay, and what happens if I am going to continue to increase the angle of incidence again? Okay, my R is going to increase again. Now I will be already 90 degrees. If I'm going to increase again, I will no longer undergo refraction anymore. I will undergo what we call total internal reflection. So now this angle I is actually greater than the critical angle C. Is greater than this original C. Okay, so you can see that instead of coming out flat at C, 90 degrees, okay, I will bend inwards. When I bend inwards, okay, my angle I will become equals to my angle R again. I will obey the law of reflection. Okay, so we say that all the rays are totally internally reflected. There is no refraction taking place, no light ray that comes out of the glass block. Everything gets reflected back in. Okay, so in general, if I shine through this red line, A, okay, at A, the light ray will just pass through straight without any refraction. Okay, at any angle between A to B, where B is the critical angle, A to B, this region, okay, as I increase, what is going to happen? Let me just draw in brown. If I have another ray that is in between this, okay, I will have refraction. So in this region, highlight to you, okay, in this entire region, okay, anyway that's in this entire yellow region, okay, I will undergo refraction. Okay, my light ray will come out in this yellow region. Okay, and then until I reach a particular angle, very special angle, okay, I will highlight in green this particular angle, okay, will be such that my angle of refraction will be 90 degrees. And this very important angle is called the critical angle. Okay, so at critical angle is still refraction. Okay, at A to B is also refraction. Okay, but what happens after this green line? Okay, if I were to increase from B to C, my light ray were to shine anywhere from B to C, okay, then I have a very special effect, and this effect will be known as your total internal reflection. Okay, I'm going to put it in purple. Okay, so let's say I have a light ray here. Okay, so I will no longer undergo refraction. I will undergo total internal reflection. Okay, and my angle I will be equals to angle R now. Okay, so what are some of the important terms that you need to know for this chapter is, okay, what is critical angle and what's total internal reflection? You need to memorize them. Okay, it's very commonly asked in exams. So critical angle is defined as the angle of incidence in the optically denser medium for which the angle of refraction in the optically less dense medium will be 90 degrees. Take note, for TIR to take place, in short, total internal reflection, we call it TIR. In order for TIR to take place, the light must be bending away from the normal. So it must be going from a denser, optically denser to optically less dense medium. So the angle of incidence is always the one in the denser medium. Angle of refraction will always be the one in the less dense medium. Okay, and then what's the definition of total internal reflection? Is the complete reflection of a light ray in the optically denser medium. Okay, because this light ray is happening in the optically denser medium at the boundary with an optically less dense medium. It must be going from denser to less dense. Okay. So the two conditions, there is always two conditions that must be met in order for TIR to take place. Okay, and every time question will ask, how come the light ray doesn't come out? That means the light ray has undergo total internal reflection, or what are the why is there total internal reflection? You always need to state both conditions. So both conditions, the two conditions are, okay, the ray or the light must be traveling from optically denser to less dense. So I can be from glass to air, water to air. Okay, but it cannot happen when it's traveling from less dense to denser. That means like traveling from air to water, air to glass, cannot. It must be from denser to less dense. So every time when you have a light ray moving out from a glass block or water, you need to take note whether there will be TIR taking place. Okay, whenever it's from denser, optically denser to less dense medium. And the second condition is that not every time from denser to less dense TIR will take place. It will only take place when the angle of incidence is greater than the critical angle. So what is the formula? There is a formula to actually calculate the critical angle. So that is the third formula for the refractive index. Okay, recap a little bit. Your refractive index, there's actually three formulas so far that you have learned. Okay, the first two is learned previously. So the first two, okay, the first one is N equals to C over V, the speed of light in vacuum over speed of light in medium. The second one is N equals to sine I over sine R, which is the angle in the air over the angle in the medium. Okay, now we are going to learn the third one. Okay, N equals to 1 over sine C. okay, whereby C is the critical angle. So every time questions that's linked to critical angle or need you to find the critical angle, or they give you the critical angle and ask you to find the refractive index, you need to use the third equation. Okay, the third equation comes about from the second equation. So the second equation, N equals to sine I over sine R. Remember, I must be the angle in the air. Okay, so for total internal reflection to take place, the angle in the air, okay, just now it's the example of the glass block. Okay, you will see that for total for critical angle, okay, it happens like this. Okay, the angle in the air is always 90 degrees. Okay, 90 degrees. So sine 90, you will get 1. So that is why I get 1 over sine. Okay, the angle in the medium is actually known as the critical angle. That's why you have this formula, N equals to 1 over sine C. Okay, next, okay, these are some of the applications of total internal reflections. Okay, we use a lot of total internal reflections in your glass prisms, in some of the lens, in some of the cameras, in some of the binoculars. Okay, so this diagram shows the binoculars one. You can just take a look in your textbook. Okay, but the more important one, we often use a lot of total internal reflection in optical fibers. Okay, what are optical fibers? Optical fibers are actually made from special materials. Okay, you have in the center, you have a material that is made of that is optically denser than the green color material, which is optically less dense. So light is always moving from denser, the blue one, to less dense, which is the green medium. Okay, what are optical fiber used for? They are usually used to transmit information, and they are often used in telecommunication and medicine. In medicine, okay, they can light is passed through the optical fiber, it will always undergo total internal reflection. They are made such that the refractive index difference between the blue medium and the green medium is very big, and such that the critical angle is very small. So when the critical angle is very small, every time light strikes it, is very likely to be greater than the critical angle. So it is very likely to undergo multiple total internal reflection. And the good thing is it's very flexible, it can bend. Okay, so this is what I say is used in telecommunication. So some of the advantage is that over copper wires is that the data transfer rate is very, very fast when you use optical fiber, and there is very little signal loss as compared to copper cables. And of course, they are lighter than copper, okay, because they're usually made of just plastic or glass. Okay, they are lighter than copper cables, and they are cheaper as well. Okay, so in medicine, okay, they are often used as endoscopes. So for example, the doctor want to inspect part of the digestive tract, like your small intestine or your stomach or your gullet. Okay, so what happens is, instead of opening up, having a surgery and then opening up, cutting out your body to check what is inside, they can actually insert just a very thin tube. Okay, this thin tube actually inside is optical fibers. Okay, and then they can just pass light and they can capture image. Okay, so images inside your stomach, inside your intestines, or inside your esophagus can be captured using this optical fiber, which is called endoscope. Okay, so it's very flexible. You can bend and twist anywhere, so it goes easily into your body. Okay, you won't feel that much discomfort. Of course, you'll still feel discomfort, but not as much. Okay, so you can capture images inside your organs without cutting up your body. Okay, another one is known as a keyhole surgery, where you use this laparoscope. Okay, so what happens is, you can see this is a laparoscope. There's a video camera attached to this optical fiber. So you just need to pierce a small hole that can fit in the optical fiber, which is very tiny and thin. Okay, just pierce in into the regions where you want to do your surgery. Okay, so you can actually, then the image, you can capture image inside your body, the part that you want to do surgery on, and then it's captured on a video camera, and this video camera will be like projected out on a TV, so that the doctor can then after that again insert a surgical instrument like a knife or sewing some needles or what to sew certain parts. Okay, then they just poke another hole, and then they can know where are they working on without cutting the body. Okay, so no large incisions can be made in the skin. Okay, so they are very small and flexible, so they can help to transmit light. It reduces pain, bleeding, and recovery. So instead of undergoing major surgery, you just poke 2 small holes, and then you can do a lot of surgery with it, because you can see what is happening inside the body without actually cutting the body up. Okay, so the advantage, thin and light, is very small for minimum invasive examination and surgery, and they are very flexible, so they can curve around obstacles and take different types of image inside your body. Okay, and another applications of total internal reflections, which is often used in a lot of cars, is in the rain sensor. Okay, so you take a look at this picture. Okay, so what happens is this is the windshield. Okay, and then you actually have a LED light that is able to emit LED. Okay, emit lights lah. So this light will hit the windscreen and then it gets bounced back. Okay, and then hits the windscreen, bounce back by total internal reflection. Okay, why is it able to bounce back? Because it's moving from, once it hits the windshield, which is glass or plastic, okay, is optically denser than air. So when it strikes it at an angle that's greater than the critical angle, there will be TIR. So it will go through multiple TIR, and then it will reach something called a photodiode detector. Okay, this photodiode detector will be able to detect the amount of infrared light that it receives. So if there's no rain, you will see that there is a lot of TIR taking place, and then all the light will go into this photodiode detector. So then the what you call that, the windshield wiper will not be activated. But what happens if there is rain? Okay, so when there is rain, okay, so now light is not moving from the windshield to air. Okay, you can see in this picture, when there's rain droplets, light is moving from the windshield to water. So compare air and water. Water is optically denser than air, so there is not much optical density difference. So you can see that not all light will undergo TIR, because now in the next example, you will see the calculation of the critical angle when there is air and as compared to when there is water. The critical angle will change. In fact, when there's water, the difference in the optical density is lesser. So when the difference in optical density is lesser, then the critical angle will become bigger. So now it's harder for the light ray to undergo TIR. So some of the light ray will come out refraction. Okay, come out as refracted rays. So you have less light undergoing TIR, and this detector will receive less light, and it will start to turn on the windshield wiper. So this is automatic. You don't need to, raining already, then I go and switch on my wiper. Okay, this one is able to detect, and then it depends on how much rain droplets. If the rain is very heavy, there's a lot of rain droplets, then there will be even more light loss by refraction. Then there'll be lesser light, and then the wiper will sweep faster. Okay, so you take a look at this example. You may pause at any point of time to interpret the questions better. So if you take a look at this example, they say that usually when you use sin I over sin R, one of the medium must be air or vacuum. But sometimes in the second case where you have rain droplets, then you're comparing rain droplets, which is water, and the windshield, glass or plastic, which is not air. So none of the mediums are air. So there is another formula. You do not need to know this formula. If they want you to use this formula, it will be given to you in the question. Okay, so this one is given that in the first medium, like this, 2 different medium, usually one of them is air or vacuum. But in this case, if one of the medium is not air or vacuum, then the general formula will be N1 over N2 equals to sine theta 2 over sine theta 1. where N1 and N2 are refractive index of medium 1 and 2 respectively. Okay, so you take a look at the first question. Okay, the first question says that if medium 1 is air, medium 2 is glass, then the refractive index of air is very close to vacuum, is 1. Refractive index of glass is 1.5. What is the critical angle? Okay, and then the next question, if medium 1 is now replaced by water. Okay, so the first one, let's take a look at the answer. Okay, so they say that medium 1 is air. So you can take a look at the previous question. Medium 1 is air for part A. Medium 2 is glass. Okay, so I'm going to jot down over here. Medium 1 is air. Okay, and then the refractive index is 1. Medium 2 is glass. And then the refractive index is 1.5. Okay, I want to calculate the critical angle. So the critical angle is when the angle of refraction is 90 degrees. Okay, the critical angle is a special angle C such that the angle of refraction is 90 degrees. Okay, get that? So I'm going to sub into the formula. N1 over N2 equals to sine theta 2 over sine theta 1. So N1, okay, which is over here, N1 is 1, N2 is 1.5. So 1 over 1.5 equals to sine theta 2. Theta 2 is over here. So sine theta 2 is the critical angle C. Okay, so it's sine C over sine theta 1. Theta 1 is over here. Theta 1 is 90 degrees. So it's over sine 90. So if I were to solve this equation, I'll get my critical angle when it is air and glass to be 41.8. This is when the light is moving from glass to air. That means no rain. No rain. There's no water. But part B, it says that if medium 1 is replaced by water, okay? So now I'm going to change. I'm going to change exactly the same steps, but I change to water. So I'm going to use another color. Okay, so medium 2 is still glass, but now medium 1 is no longer air. It becomes water. And then my water refractive index is 1.3. It's no longer 1 because I changed my medium 1. Instead of air, it becomes water. That's what's stated in the question. Again, I want to find the critical angle now. So again, I want to use the formula N1 over N2 equals to sine theta 2 over sine theta 1. So I get N1 is 1.3 over 1.5 equals to sine theta 1. Sine theta 1 is again the critical angle. Sine C over the sine R. Sine R, if I want to get critical angle, sine R will always be 90 degrees. So in this case, if I'm moving from glass to water, okay, means got rain, got rain. Okay, my critical angle becomes 60.1. Can you see that my critical angle becomes bigger? In order for TIR to take place, in order for the light to not come out of the windshield to bounce back to the sensor, I need, when it has rain, got rain, I need the angle to be greater than 60.1. If there's no rain, I only need the light ray to be bigger than 41.8. Then my sensor, I will have TIR, my sensor will take place. My sensor will detect a lot of light. But now I need to be 60.1. Then my sensor, then I can have TIR, then my sensor can receive it. So actually there's less TIR taking place because I need to hit above 60.1, get TIR. So now it's very hard to hit 60.1. So I have not so much TIR. So I will have less light reaching it. So if you go back to here, So the rain sensor, part C, the rain sensor distinguishes between a dry and wet day by the amount of infrared light received by the detector. If the infrared light is not to undergo TIR, what is the conditions that must be applied to the angle of incidence? So if I want TIR, okay, so to have TIR, I must be greater than C. But now I don't want it not to undergo TIR. Okay, not to undergo TIR. If I don't want it, then my I must not be greater than 60.5. So you can see the beam angle of incidence must not be greater than 60.1. If more than 60.1, TIR will take place. Okay, and okay, next example. Okay, an optical fiber is used to transmit light by total internal reflection. And then they say that the fiber core has a cladding layer. So this dark blue is the core, the main part. And then there's an outer layer called the cladding layer, okay, which is the light blue part. They ask you, why must the cladding material have a refractive index that is lower than that of the core? So if I have a refractive index that is lower, that means this one is less dense, less optically dense, because it's lower refractive index, so less optically dense. I am asking you why this cladding must be lower refractive index. Okay, the answer is because in order for optical fiber to be used to have TIR, total internal reflection, light must move from denser to less dense medium. So I must have light moving from denser to less dense medium in order for a lot of TIR to take place inside. Okay, next one, explain why the angle of incidence must not be too large. So the angle of incidence is here. Okay, you should know that if I were to increase the angle of incidence, then my angle of refraction, which is here, will also become bigger. If my angle of refraction becomes bigger, what is going to happen? Then my angle, okay, I go to the answer key over here. So the conditions for TIR to occur is that light must rally from optically less dense, from denser to less dense medium. Okay, so the cladding must have less dense medium, must have a lower refractive index. Okay, so if you can see over here, if my theta increase, then my angle of refraction will increase, and then this theta I, the angle of incidence in the denser material over here, this blue ray, will be smaller. Okay, so the angle theta I will get smaller. And if theta I is too small, TIR cannot take place, because in order for TIR, this theta I must be greater than the critical angle. Okay, next one. Part C, they ask you, suggest an example of how is it useful in medicine. Okay, you should have known that it's used in endoscopes and laparoscope, okay, to channel light into an area inside the body to generate image, so we do not need to do large-scale operation. Okay, and then part D, they just ask you to draw total internal reflection that takes place inside the optical fiber all the way until it exits. Okay, you just need to make sure that the angles are almost equal, because for TIR to take place, I must be equal to R. Okay, so you just draw multiple TIR all the way until it exits out of the glass cladding.